Welcome to my video. In this video, what I'm going to do is I will be explaining the question that was provided. It falls under the Affinity. It's an application of Affinity laws. So please make sure that you leave your comment, like, and subscribe on this channel. And thank you very much. So now, without wasting any time, let's jump to the question that was sent in order for us to make sure that we understand this question. Now, this was the homework on slide number 67. So now the homework goes as follows. Let us read it together. They say to us, a pump draws water at a velocity of 1 meter per second from a tank and delivers it to another with the surface 8 meters above that of the lower tank. Right, so that means the delivery pipe is 30 meters long, 100 bore diameter, and has a friction coefficient of 0.003. The pump impeller is 500 millimeters diameter and revolves at 600 revolutions per minute. The pump is geometrically similar to another pump with an impeller of 550 millimeters diameter, which gave the data below when running at 900 revolutions per minute. So basically the data below provided over here is for pump number 2. Right, so now for pump number 2, we have the change in head, which is provided to be this, and then for flow rate, we have different flow rates for pump number 2, which are provided to be this. Now they want us to determine the flow rate and the developed head for the pump. So that means that the impeller diameter and rotational speed required assume a friction factor of 0.005. So in this case, what's happening is we are focusing on pump number 1. This is the question that needs us to focus on pump number 1, right? Determine the flow rate and developed head. We need to do that, but for pump number 1. But basically, in order for us to do that, we're going to apply affinity laws so that we can be able to solve this question. Right. So now in this case, what's happening is let us write the given information down so that we can understand how are we actually going to use the information. So now the data that is provided to us, we are actually given number 1. Let's talk about pump number 1, right? I'll say P1. Under pump number 1, we are actually given the diameter of the pump. So the diameter of the pump, it is provided to be this one, which is 500 millimeters, right? And therefore we are also provided with the rotational speed. The rotational speed is, where is it? The rotational speed, it's 600, right? It's 600 revolution per minute. So the rotational speed for pump number 1 is going to be 600 revolution per minute. And then we are also provided with the velocity of pump number 1 to be 1 meter per second. So velocity of the pump, it is 1 meters per second. And let's have a look at the height, right? We are provided with this, which acts as a height, right? Which is the height, right? So meaning they say from a tank and the deliveries, it is to another with the surface of 8 meters above that of the lower tank. So meaning our h over here height, it's gonna be 8 meters, right? And we are also provided with the length of the pipe, right? The length of the pipe is 30 meters. You can see over there. And we are also provided with the bore, the diameter bore, right? They say to us, we have the delivery pipe is 30 meters long, 100, here's supposed to be 100 meters before bore diameter and has a friction coefficient of 0.03. So we are given the diameter bore to be equals to 100 meters. Yeah, it's supposed to be 100 meters there. See, millimeters. I believe. Sorry about that. I fix that quickly. Okay, so we have 100 millimeters. And therefore, we are also provided with the coefficient friction, right? What is it? It's our F in this case is going to be equals to 0, 0, 0,003. And then that's it. And then for pump number 2, what are we provided with? For pump number 2, we are actually provided with diameter 1, and then the diameter 2. In this case, our diameter 2 will be 555 millimeters, and then the rotational speed, N2 in this case, up to will be 900 revolution per minute, right? So this is the only information provided at this point in time. Oh, by the way, we are also provided with this frictional factor, which I assume that we're not going to use because we have already provided with the frictional factor of the bore pipe, right? Of the bore diameter. So now this is the information so far that we are actually provided with, right? In this case, to answer the question, remember what we need to do. We need to determine the flow rate and the developed head for the pump, meaning referring to pump number 1. So in this case, we have the flow rate for pump number 2. We also have the height for pipe number 1, for pipe number 2 as well. So to apply the affinity laws, what I'm going to do is, let me change to a different slide. So what I'm going to do here is to apply the affinity laws, I'm actually going to talk about the flow rate. Right? We know that using the flow rate, I can use Q2 over Q1, which is equals to, here we use the ratio for diameters, right? We have D2 over D1. So how I remember that here is to the power of 3, because I remember flow rate, it's M to the power of 3, multiply by, using the units, right? Multiply by, here it's my meters again, it's my seconds again, right? But for the fact that I'm using rotational, so it's going to be N2 over N1, right? Remember, N basically it's per second. So how many per seconds do I need? I need only 1 to calculate the flow rate. Remember, to calculate the flow rate, it's the units so that we use is meter cubed per second. So to apply this affinity laws, I know that here I'm going to use my diameter, which is in meters to the power of 3 over there. And then here I know I'm going to use my revolution, which is per second, which is to the power of 1 over there. So this is the hack on how to remember these formulas or equations. So now in this case, remember we are provided with D2, D1, N1, and N2. And then Q2 is a little bit complicated, but it's a little bit complicated because it's provided in this form. Q2, we have main values of Q2, right? So meaning we're going to calculate for each. So in this case, I am going to have Q2 over Q1, which will be equals to my D1 in this case, it is 0.55 because we had to divide D2, which is in millimeters. Remember the SI units, we use the meters. So we're going to have to divide this by 1,000. So that means we're going to get 0.55 meters divided by our D1 is going to be 0.5 to the power of 3 multiplied by our speed N2 in this case. It's going to be 900 revolution. So that means we're going to have 900 revolution divided by 600 revolution per minute. So the thing is, even if you actually really do not divide that, you're still gonna get the same answer at the end of the day because you are dividing, even if you didn't convert it. So it's still fine, okay? So now here we're gonna have Q2 over Q1. In this case, when we punch everything on our calculator, we're actually gonna get this to be 1,9965, right? So what we're going to do here, because we are looking for flow rate for Q1, we're going to make Q1 the subject of the formula by saying Q1 is going to be the same as Q2 divided by 1,9965. So this is Q1. Remember, in order for us to determine Q1, we're going to have to use Q2. But like I said, we are given the complex values of Q2. So that means for each Q2 that we're going to substitute on that equation that we have just derived over here, we will be able to get the flow rate for Q1. So in this case, to get the flow rate for Q1, what I'm going to do is I'm going to substitute 0 here because the first value for Q2, it is 0. So when I substitute 0, I am actually going to get 0. Right, and then the second value for Q2, it's 0.016. So that means I'm going to have to substitute 0.016 over there, and what I'm going to get on my calculator, divide by this, I'm actually going to get 8.01 times 10 to the power of -3 meter cubed per second. And then I'm going to do the same with this value, this value, this value, this value, this value, and so forth. So already calculated, what I got was 0.016, right? And then the another value was 0.024, and then the other value was 0.032. The other value was 0.040, and the other value was 0.048, right? So that means we managed to answer the first question where we needed to determine the flow rate applying the affinity laws for Q number 1 using Q number 2. Now, the second question was to determine the developed head for the pump, again for pump number 1. So what we're going to do here, again, we're still going to apply the affinity laws. But when we apply the affinity laws, we're going to have to take account for the frictional losses that is taking place in this case. So in this case, what we're going to do is we're going to talk about the head losses, right? Head loss for pump number 1 again, applying affinity loss. So to calculate the head loss, what you're going to do is we're going to say head loss, change in H2 divide by change in H1, which is going to be, we know that head loss, it is given in meters, right? But here, because we are using the diameter and what is this thing? The speed, the rotational speed. This one, the trick is for you to remember it. You only use squared, right? So here we have the diameter, which is d2 over d1 to the power of 2. I know that the head loss, normally it's meters, right? So this one is a little bit tricky and it will complicate your life by thinking why here, because I have diameter, it's supposed to be meter squared, multiply by our speed here, it's going to be n2 over n1 to the power of 2. Meanwhile, here you're going to have revolution per second and you expect it. So it's fine. This one, just remember that you use 2 squares, squared, that's it, okay? So in this case, what you're going to do, again, we're going to perform a substitution. Change in H2 over change in H1 will be equals to, now our diameter, remember it's 0.55 for D2, right? And then for D1, it's 0.5 to the power of 2, multiply by the speed, rotational speed. Remember, we had 900 for N2, and for N1, we had 600 to the power of 2. And then when you punch this on our calculator, we're going to get that the ratio for H2 over H1 is going to be already calculated. I got my 2,7725, right? Therefore, after calculating this, we're going to make H1 the subject of the formula by saying delta H1 is equals to delta H2 divided by 2,7725. Again, remember for H2, I am given these numerical values over here for pump number 2. The pump is geometrically similar to another pump with an impeller of this, which gave the data below. So that means this is for pump 2. So H for pump 2, the first value is 37. So what I'm going to do, over there is I'm going to have to substitute 37 over here. Oh, by the way, let's not forget that our units over here is going to be cubic meters per second. Okay, just wanted to fix that. So again, here to determine delta H1, what we're going to do is we're going to start by substituting um individual values for H2, right? The first one, like I said, it was 37. So we're going to have to substitute 37 divided by 2,77, 2,7. Oh, yeah, it's supposed to be 2, I guess. Can confirm it with your calculations. Yeah, it's supposed to be 2. So 2,7225, and then there we divide by 37. The first value that we're going to get will be 13,5959 already calculated. And then we move to H2, which is 41, right? So you're going to substitute 41 over there, and then I got 15,06. Lastly, we're going to move to 44, 45, 42, 36, 28. We're going to move by substituting all of those values onto this equation, and therefore we're going to get 16,16, and the other value is going to be 16,53, and then the another value it's going to be 15,43, and then the other value is going to be 13,22, and then lastly we're going to get 10,28. And therefore the units for the height, we know that for head loss, it's going to be meters, right? So in this case, we are actually not done in calculating the head loss. Okay, we are not done in calculating the head loss because we have to consider the information provided to us. They say to us, number one, we need to calculate the developed head loss for the pump, meaning we need to calculate, or is this? We need to calculate the developed head loss for the pump, meaning we need to determine the total developed head loss for this pump, which is pump number one. But under pump number one, we were given some information that shows that we do not ignore other factors, right? Such as, let's have a look. I'm gonna redo this so that you can understand why am I saying we are not done in determining the head loss for pump number one. For pump number one, remember they said to us, a pump draws a water at this velocity from a tank and it delivers to another with a surface of 8 meters. This will lead to head loss as well above that of the lower tank. You see, because we have to lift the water from the lower tank. So above it, we're going to have 8 meters as our head loss, right? Our first head. The delivery pipe is 30 meters long, right? It has the length of that pipe, number one. Number two, it has the diameter, and then it has the friction coefficient of this value over here. So using this information only, U, H, L, D, and F, they're going to help us to determine the friction, to determine the head loss of pump number one, right? So what we're gonna do here is for pump number one, we're gonna have to determine the head loss first, right? The head loss first. So now the head loss in this case, we're gonna use the equation that says friction multiplied by L over D multiplied by U squared, which is velocity, divided by 2G. So our friction was given to be 0.003, right? And therefore our length of the pipe, it was 30 meters. And then our diameter of the height was 100 millimeters. So we divide that by 1,000, we get 0.1, and then our velocity was given to be 1 meter per second to the power of 2, and therefore we have 2 multiplied by our gravitational acceleration is 9.81 meters per second squared. And then when we punch this on our calculator to determine the head loss already calculated on my side, I got, let me see, I got 0.046 meter. Meters. That's what I got. So to determine the, I'm going to utilize this space over here. To determine the total head loss, we're going to use the head loss for pump number one. We're going to use the head loss for pump number one. We're going to use the head loss that we have just calculated due to the length of the pipe, due to the diameter and the velocity and the coefficient, right? And then we're also going to include the H, which is 8 meters. because that also leads to the head loss of the pump. And therefore, to do this, remember for delta H1, we have various numerical values, which are these. We have 13,59, 15,06, 16,16, and so forth. So for delta 1, we're going to add these values, meaning 13,59 plus HL. HL is 0,46 plus H. Remember, our H in this case was determined to be 8 meters. So that means what we're going to do here, we're going to add 8. Remember, this is going to be delta H1 plus 0,46 meters, 0,046 meters plus 8 meters. So I'm going to add all of these values individually. So what I'm going to get for H total in meters as well, it's going to be as 13,59 plus 0,046 plus 8 meters. And then on my calculations, I got 21.64. And then again, 15,06 plus this number plus that number over there, right? I got 23.11 and so forth. We consider this again, 16.16 plus this plus that. And then this is what I got. I got 24.21, and then the other one I got 24.58. The other one I got 23.48, and the other one I got 21.27, and then the last one I got 18.33. And therefore, now we managed to answer the question. So the question that we answered, the first one, the second one is this one, and then the first one was this one over here. Then that's how we go about in solving this question. And thank you.